So please remember that in circuits the long line is the positive terminal and the short line is the negative, and electricity is set to go in this direction here through the ammeter, which measures the current, and then goes through the two light bulbs as shown, and both light bulbs should obviously light up. Okay, and then in the second diagram the light goes from positive to negative, but it can go one of two routes. It can go through both circuits in the same way, but it can take two rows instead of one. So both light bulbs shine separately. Okay. Now the advantages of the parallel circuit is that if I was to put a break in this circuit here, it'd mean that the second light bulb would go out, but the first light bulb would stay on. However, if I put a break in the first circuit, both light bulbs will go out if there's a break in the first circuit. Okay, so which one is connected in series? X is connected in series because it's one after the other. The second one's connected in parallel because there's two parallel circuits, two parallel lines, this line here and this line here together. Okay, and they both have two separate bulbs and two separate wires. Okay, name device A. Device A is an ammeter. Okay, which one will the bulb be brighter in? Well, as it turns out, because the current has to go through two bulbs in series, it slows it down and makes it less bright. So the parallel one will be brighter because each individual electron only has to go through one bulb, while in the first circuit each electron has to go through two bulbs. So imagine I'm this green electron here. When I travel around this circuit, I have to go through one bulb, then I have to go through the second bulb, and this slows me down and makes the current less fast. Well, if I'm a green electron in the second circuit, going from positive to negative, I can either go through the one bulb that way, or I can go through one bulb this way. Okay, so they're brighter in circuit Y. And then if one bulb is unscrewed, no bulb will light. That's true for circuit X. If we break the connection, that means it breaks the connection for the full circuit. Okay, next one. If a bulb fails in circuit A, does the second bulb stay on? Yes, it does, because it's a parallel circuit. So when the circuit is closed, if there's a break in one bulb, what will happen is I can simply go around through the second bulb instead. Is that alright, guys? So what I can do is, if there's a break in one bulb which has the red line there, what we can do is we can go around the second bulb and light the second bulb. Okay, does it stay on? Yes, reason being, parallel circuit can go through the other bulb. Current can travel through the second bulb. Second bulb. Okay, if a bulb fails in circuit B, does the second bulb stay on? The answer is no. Reason, if one bulb blows, the circuit, there's no way to complete the circuit. The symbol phi is for a meter that measures potential difference, often called voltage. What is the electric quantity that can be measured using the meter with symbol A? What can be measured is the current. A measures current and B measures the volts. And current is measured in amps, so it measures the current. Okay, let's move on to the next one. Put A or V. Okay, so the main thing you need to know about this circuit, now this circuit might not be asked in your summer exam because we didn't really have to go this far, but I just want to make sure we know what we're doing. A is always connected in the way of the electrons, okay? So for A to work, to measure the current, a blue electron has to travel through it, okay? And complete the circuit that way. Voltmeters, however, are always connected in parallel to a resistor if they're measuring the resistance. So this voltmeter is measuring the voltage across the resistance, right? So A is always in the main circuit, but V is usually parallel to an individual part of the circuit. Now, if you're asked to calculate the resistance, which I believe you are, next page, calculate the resistance. Resistance equals V over I, a voltage reading divided by a current reading. So I think we'll go for this point here. This is a current reading of 0.5 and a voltage reading of 6. So we have 6.0 on 0.5. So voltage divided by current will be 6 divided by 0.5. Put that into your calculator. 6 divided by 0.5 and you get 12 volts. Okay, give one safety precaution taken by the pupil shown in the photograph. You could say that he's wearing goggles. Glassware is in the middle of the table. I believe he's using a tongs to hold the test tube. You name it. Describe a precaution not shown in the photograph. I don't think he's wearing gloves. Not wearing gloves. Or a lab coat. Anything you can think of, really, guys. Okay. Question 5. Name the two items. Name any two items in this. Well, you have your Bunsen burner. You have your tripod stand. I think are the two main ones. Tripod stand being the tree and that being the Bunsen burner. Can't really make out the other ones. So I'm gonna leave it. Okay, they're the two main ones. Okay, question 6. A group of students were investigating how solubility of water changes with temperature for solid compounds 1, 2, and 3. The graph below shows the results obtained. Hot water is needed for this investigation. Name an instrument used to heat water in a laboratory. Bunsen burner. Or kettle. Or hot plate. Whatever you want to use for that. Describe one safety precaution which should be taken when heating water in a laboratory. To wear goggles and to use tongs to handle the hot glassware. Or an oven mitt, even an oven mitt, if you didn't have that, okay? Or oven gloves, something like that, to avoid you getting burnt off the hot glass when you have to move the objects, okay? Now, next part here, we have a diagram of A, B, and C. Now, let me describe what this diagram actually means. So, what we have here is, if we take the first, the red diagram, down here, at 0 degrees, you can dissolve, let's say, 4 grams of salt in this solution, okay? Now, at 50 degrees, go up and across, see you're roughly at about, so what I'm doing is every time I'm going up and across to see what's going on. So roughly at 50, you can do about 18 grams, okay? So at 50 degrees, you can roughly do 18. And then let's say at 100 degrees, we can roughly do 45 grams of salt. So you can see as the temperature goes up, you can dissolve more and more salt. Now for the blue one, it's 0.5, which means at the very beginning you can dissolve 5 grams of salt. At 50, it's around 15 grams. And then at 100, it's around 25 grams of salt. So you can see the blue one doesn't rise as quickly as the red one, but still rises. Now the green one's a bit weird. At the very beginning, when it's 0 degrees, a very cold solution, you can only dissolve 25 grams of salt. At 50 grams, you can probably only dissolve around 26 grams, so it's barely moving. And then at 100, it's roughly around 27. So it doesn't matter how much temperature you put in, you're not getting that much extra grams of salt you can dissolve in that. Okay, so the general trend is the solubility increases with temperature. Which compound shows the greatest increase in solubility from 0 to 100 degrees? Well, it's safe to say that's the red line. And the red line is, which compound is the red line? Is what we should probably figure out. 1 second. Pause this. Compounds are in the diagram, so it's compound 3 or salt 3. You can dissolve 45 grams of compound 3 in 100 milliliters of water when it's at 100 degrees. You can dissolve 18 grams of compound 3 at 50 degrees in 100 milliliters of water. On the graph, circle the point where compound 2 has the same same solubility as compound 3 here. So we'll just highlight it in purple. There you are there. Okay, state one advantage of presenting scientific data using a graph. It can be easy to compare different solubility rates. Of different compounds. So the graph helps us to compare the different solubility rates of different compounds. Okay, and that's us done with that one. F. Student carried out an experiment to investigate the solubility of copper sulfate in water. So copper sulfate is the blue crystals, and what happens is you want all the crystals to disappear and for them to make a blue solution. So you shouldn't be able to see any crystals down the bottom when they're all dissolved. Describe the effect of increasing the temperature on the solubility of copper sulfate. It increases the solubility. It increases the amount of copper sulfate you can dissolve in water. Okay. To prepare crystals, a solution needs to be saturated. Describe how to make a solution saturated. Keep adding in solute or crystals or copper sulfate into solution until no more solute can be dissolved. Basically, a saturated solution means you can't dissolve any more crystals. So let's say, for argument's sake, I'm going to put them in red. Anytime I drop crystals into solution, they basically disappear. But when I drop the last one in, it won't disappear. This means that you have a saturated solution because the water is incapable of dissolving the last bit of solute or crystal you put in, if that makes sense. Okay, question 8. A group of students investigate the solubility of different substances in water. What's the term used to describe a liquid such as water that's used to dissolve a substance? It's known as a solvent. While investigating the solubility of copper sulfate in water, the students found that adding a large mass of copper sulfate to the water, some of it did not dissolve even after shaking and stirring. What term could you use to describe a solution that contains as much dissolved material as possible? A saturated solution. Okay, we just went through it a second ago. Outline the steps the students could have taken to make more of the copper sulfate dissolve. They could heat the water, or they could add more water. to the solution. Heating the water increases the energy and enables you to dissolve more copper sulfate in a given quantity of water. So if you had a litre of water, by heating up the water, the litre can dissolve more copper sulfate. Or if you haven't got the ability to heat, just add in more water and that will help dissolve it. Okay. A science student investigated the solubility of two common substances, sugar and salt, in water for a range of temperatures. The data for sugar are given in the table. Salt maintained a constant solubility of 40 grams to 100 grams of water for the temperature range investigated, 0 to 100 grams. So salt didn't change at all. Okay, so that's interesting. So what we're going to do is we're going to draw a graph of the solubility of sugar in the grid below. So we're going to have to draw the sugar. So it shouldn't take you too long to get this done. Okay, let's see what we can come up with. Now, 175 will be halfway between 150 and 200. 200 is 2200. 40, 240. So 240 would be, there's 5 blocks. See that? 1, 2, 3, 4, 5. So each block's worth 1. So 40 would be just one mini block underneath the 250. 60 is 290, which is around there. 80 is 370, so 370 would be 3 blocks underneath 400 or 2 blocks above 350, and 480 will be 2 blocks underneath 500. Okay, you see it's a curve, not a straight line. And there you go, there is your curve. Done. What's the next thing they want from me? Use the graph to estimate the increase in the solubility of sugar from 50 to 70 degrees. Okay, so 50. Let's go to 50 degrees here. We use a dotted line. 50, which is 270, and 70, which is around 320. So I'm doing 320 take away 270. 320 grams per, how much water? Per 100 grams of water. So it's 320 minus 270, which is 50. You can dissolve an extra 50 grams per 100 grams of water. Using the same grid, draw the effect of the temperature on the solubility of salt. Well, we're told that the salt stays at 40 grams all the way through. So salt will represent with the green line. Just stays at 40 all the way through. So here's salt, and there it is. The green line represents salt, just stays at 40 all the way through. Okay, done. Next one. The diagram shows 3 solutions of copper sulfate. Start with the dilute solution. Say how to make it more concentrated. Add more solute slash copper sulfate. Until no more can be dissolved. Okay, how do you know when a saturated solution has been produced? No more solute or copper sulfate can be dissolved. Sorry guys, in the first one I actually didn't state the correct answer there. Add more solute to the mixture is just the answer. You're just looking to make it add more solute to the solution. You're actually just looking to make it more concentrated. You're not looking to make it saturated. So that's my fault. So that's the answer. add more solute to the solution. Okay. Now A, distinguish between a concentrated and a dilute solution. Concentrated solution has a higher mass of solute dissolved in a given volume of solvent, while generally dilute solutions have a low mass or low amount of solute dissolved in a given volume of solvent. Okay. Now, solubility of salt, ammonium chloride, and water. She determined the maximum mass in grams of the salt that would dissolve in 100 grams of water at various temperatures. The data from the experiment is given in the table. Okay, so I'm obviously going to have to draw this, which ain't great. So let me see what I can do with this. Shrink it down for a start. Shrink it a bit more. Okay, so have to go from 0 to 77 on this axis. So let me see what I can do with this. I'm going to make every 5 blocks worth 10. Hopefully that will work out for me. 20. Hard on the eyes, this. 30. 40. 50. 60. 70. And that can be 80. So every 2 blocks is like 72, 74, 76, 78, 80. So remember, it goes up in 2 blocks. Now I have to go up in 20s on the bottom. Shouldn't be a big issue at all, actually. You can just do it. Will that work? 20, 40, 60, 80, and 100. Yep, that will work out nicely. Time to plot the graphs. So 0 and 29, so just around there, just underneath the 30 mark. 20 and 37, so just underneath the 38 mark. 46 and 40, so 40 and then 46 is 3 blocks above that. And then 55 and 60, so 60 there, and 55 is halfway between 50 and 60, so around there. 80 and 66, 66 is 3 small blocks above the 60 mark, and then 100 and then 77, which is around there. This one actually looks pretty close to being straight. Wonder what the gaps are. 18 for the first gap, 19 for the next gap, 21, 20. Sorry. I'm completely wrong there. 8 for the first gap, 9 for the next gap, another 9, and then an 11 and an 11. So part of it is a straight line. This part here is straight, but then the other parts aren't. So you gotta do like a curve. So only part of it is straight, and then the other parts, it's pretty close to being straight, but it's not quite straight, which is unusual. You could probably go back and probably do this with a sort of like so close to being straight, but not quite straight. Alrighty. So what's the next thing they want from me? Use your graph to estimate the solubility of ammonium chloride at 70 degrees. So I need to go to 70 degrees. Grab 70 degrees is halfway between 60 and 80. And I'd say it's roughly, go straight up, straight across, I'd say 60 grams per 100 grams of water. 60 G per 100 G of water. What conclusion about the solubility of ammonium chloride can be drawn from analysis of the graph? More ammonium chloride can be dissolved in water at a higher temperature. At higher temperatures. Or a greater amount of ammonia chloride can be dissolved in water at higher temperatures. Okay. Question 12. Students were given a mixture of sand and salt, and they were asked to separate the mixture in the laboratory. First, the mixture was added to hot water. What happens to the salt at this stage? Salt dissolves in the water. The next stage of the experiment is to remove the sand. Sand and salt. So the salt dissolves in the water, but the sand stays. Sand is mixed into the water, but the salt is actually dissolved in the water. So, okay. The next stage experiment is to remove the sand from the mixture. What separation technique can you use? You can use filtration. So essentially, if you imagine this as a filter paper, imagine these gaps like a gate. Okay, the salt particles and the water particles are blue, and for argument's sake, the salt particles are purple. Okay, and the water and the salt can get through the gaps, but the sand particles are too big. So these are the sand particles in the water. Okay, so the water gets through, no bother. The salt gets through, but the sand gets stuck in the filtrate, okay, in the filter paper. Okay. Now, what can we do next? Don't seem to be able to scroll down these days, which is quite annoying. Okay. What the final stage of the experiment is to get the salt on its own. What separation technique? So what you can have is you have salt water underneath. After you filter it, you have salt water in a container. Okay, so it comes down and you have salt water. And what you can do is you can evaporate off the water, and you can evaporate it. You can put it into a glass, into a evaporation dish, put it onto a tripod stand with a Bunsen burner, and what happens is the flame will evaporate off the water, leaving the salt behind. So you can use evaporation. Okay, happy days. 13. Now, what's up with 13? Just about labeling the apparatus, so it shouldn't take that long. Name the separation process shown. It's distillation. Name the piece of apparatus labeled C. It's known as a Liebig condenser, or just a condenser. It's a water jacket that cools the steam into water. Name the change of state that occurs in C. Well, it's a gas, so it's water vapor. Turns into gas to liquid. Now, that's not actually naming it. I actually would have got that question wrong. It's condensation. Condensation. Where gas turns into a liquid. Which arrow A or B points to the location of the impurity X? So at the beginning you had water with the purple impurity, okay, and the water is the blue dots. So you have the blue dots mixed in with the purple dots. The blue dots come up here as water vapor, which is a gas. They enter the cooling tube where they turn into a liquid, and then they flow into B. So the pure water's in B, but what gets left behind is the impurity. So it's in A. Okay. Now, 14. Two students have just separated seawater from salt. Name a suitable method for this. Evaporation. How could the salt be separated from the seawater? By boiling the salt away off the water. Okay, it's an interesting one. How could it be done? One sec, there is no 15 underneath. So how? By placing the water in an evaporation dish and heating the dish to over 100 degrees to evaporate off the water, leaving the salt behind. Okay. Question 15. Paper chromatography is used. The same liquid, paper, and pens were used in each of the three experiments as shown. They started at different times. So first A, then B, and then C. So I think the analogy I used for you guys was a bit like a surfer. Let's see if I can now scroll down. Nope, it doesn't let me scroll down anymore, which is really annoying. Okay, so imagine that it's like a wave, and this is the surfer. And what happens is the water rises up. Sorry, the water rises up the paper. Okay, what happens is it contacts the red dot. What happens is it dissolves some of the red dot, and then some of the red dot stays behind. So it's a bit like, imagine 100 surfers riding a wave from start to finish. Some of the surfers fall off along the way, so you get some red patches along the way, and then as the wave travels up, it releases more and more of the surface. Okay, and then eventually at the very top, your last surfer maybe falls off. So you get like a display of it basically catching the wave is the marker getting dissolved by the water, and then when the surfer falls off, that's the solute falling out of solution and being deposited. So basically it gets the marker, dissolves it, and brings it up the paper, where different parts of the marker fall off at different times. Now, why is the ink level of the what is the ink dot above the level of the liquid in each beaker? So that the water level can rise to meet it and bring it up the paper. What caused the dots of ink in paper B and C to spread upwards? The marker was dissolved in the water. In the water that was traveling upwards. Traveling upwards. Okay. Why were colours other than brown seen in B and C as the ink moved up? Some colours like brown are made of many other colours. So basically, it was a brown marker. Hopefully that's brown. All right, so it was brown, but then brown can be made up of a yellow, a bit of green, and then a bit of red. So you don't really know. It could be a mixture of different colors. Okay. All right, guys. I think that's that one done. A mixture of sand and salt were it was stirred up with water and then filtered as shown. Substance A was retained in the filter paper. Name it. It could be just the sand. Some people might call it the residue. So it's a difficult question. I'd put down both, sand or the residue. Substance B is known as the filtrate, or it could be just salt and water. So I think they were looking for salt and water there because they wanted one constituent of it. So constituent B was salt and water. Okay. Question 17. Happy days. Nearly there. A spot of water-soluble ink was put on a piece of chromatography paper and set up as shown. What happens to the ink spot as the water moves up the paper? The water dissolves it. The water dissolves the ink. And spreads it upwards throughout the paper. What could happen to a spot of water soluble consistent of a single colored dye if we're using the above experiment? It would only separate out into one color. So remember, brown separate out into many colors. A single dye would only separate into one color. Okay, and we're done. So that took 36 minutes.